Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Sorry about that. It is our great pleasure and honor and privilege to have Kevin Fu with us today. Kevin is no longer, I hope, a doctoral student at MIT's Department of EECS, but maybe still for another month or two.
Defended, but I'm a pre-doc.
Okay. Still nominally a doctoral student at MIT's Department of EECS, and member of, and possibly product of, MIT's Computer Science and Artificial Intelligence Lab, and a visiting scholar at the Johns Hopkins University Information Security Institute in beautiful downtown Baltimore, Maryland. His research interests include computer system security, secure storage, RFID security, and web authentication. Kevin holds in his hand right now as we speak an SB, whatever that is, in computer science and engineering, and a Meng in electrical engineering and computer science from MIT. He also, he was, by the way, he was born in West Virginia, right? And grew up in West Virginia, which he tells me is cheaper because you don't have to have shoes. Kevin also holds a Certificate of Achievement in Artisanal Bread Making from the French Culinary Institute and the CIA, correct?
Right.
Yes. And he earned a minor in Latin, which fortunately he will not be using very much during the talk. Please welcome Kevin Fu. He will be speaking about secure content distribution using untrusted servers. At least that's what his first slide says.
Yep. I could talk about the baking if you want, but I was really hoping to open a restaurant one day like the Fu Bar and Grill. Okay, so today I'm going to talk about how to achieve secure content distribution if the entire infrastructure actually physically replicating the content is untrusted. So we're going to have publishers producing content, readers who want to get access to the content. The readers want to verify the authenticity of the content. Often the publisher will want to maintain some kind of access control, but the link from publisher to client is going to be completely untrusted, and we'll just assume malicious parties are controlling the network. Okay, so for the talk, I'm going to use a slightly whimsical example of I have a graduate student, and she's sitting at home on a cable modem which has very low upload bandwidth. So the job of that she wants to get done is she wants to say have her popular open source software or a popular blog be distributed to lots of readers, but in an authenticated manner and not be constrained by the local networking resources. So there are a couple straightforward ways you could get sort of good content distribution. The easiest way, if you're a company, is you just throw money at the problem. So you can pay a service provider to replicate your content all over the internet, which is a perfectly reasonable solution. Maybe not if you're a graduate student. If you have to choose between, say, food and content distribution, you're probably going to go for food and lots of it. But another alternative, if you're in this case of being sort of a poor publisher, is, well, this was around Valentine's Day when I had this on my mind, and the Necco factory was very close by. So you could ask your friends to replicate your content. You can ask them, please take my content, replicate it all over the place. But again, as a graduate student, they tend not to have the best social skills, at least that I found. So it might be difficult to find sufficient friends to, satisfy your number of readers. Yes. But fortunately, actually, there are volunteer content distribution networks. So if you have very popular content, folks can actually use these volunteer systems to replicate your content all over the internet. I find that when I was a resident tutor at MIT, the undergraduates were intimately familiar with BitTorrent. But these are popular ways to distribute content. But you as a publisher, you don't really have to pay for your own local throughput, your own local bandwidth. You can actually cope on just trickling your data out. So those three kind of ways to do content distribution are great ways to actually get the distribution, but it doesn't talk about how to actually get security semantics. There, I used the word semantics. So what I'll talk about is how we're going to build an architecture that is going to make sure the content can be authenticated, and if the publisher wishes, can also make the content access controlled. And it's fairly straightforward to do that, but the tricky part is going to be doing that efficiently. So I'll talk to you about some efficient mechanisms I've designed and built and measured. So I was sneaking ahead into my last slide. But the basic idea, skipping around on this slide, is that our servers are going to be untrusted. I'm just going to assume that malicious parties control the network, and I'm going to see what can we get, what's the best we can do as a publisher trying to push out some content. So on the client side, the client's probably going to want authenticated content. So as an example, and it's probably important to Microsoft, would be software updates. You want to make sure that if you're a user updating your Windows XP system, you want to make sure you're actually getting the real deal and not some horrible other software like I don't know, a Macintosh operating system, or virus definition files as well. Now on the publisher's side, for private content, the publisher may want to control access. So one example would be an online newspaper. The Wall Street Journal, in fact, is an access-controlled system where if you pay, you can get access to the content. So I want to know, how can a publisher do access control when, again, the untrusted servers cannot even be trusted to, say, mediate access? You can't even trust them to check whether a user is authenticated. Is there something wrong with the slide? You're smiling. But, yeah.
I'm a happy guy.
Oh, okay. I was afraid I spelled something wrong. But, okay. So for the rest of this talk, I'm going to talk about a very specific kind of content, and that's content distribution content. So this is going to be different from your traditional file system, because I'm talking about file systems, but at the same time, I'm talking about content distribution. So the reason why it fits is my file system handles only single writer, many reader content. In other words, a single publisher produces the content. Nobody else gets to do the content updates, but then many people can read it. And then I further divide the problem into two areas of how to handle the authenticating public content, and then later I'll talk to you about how to additionally provide access control when that content is private. Okay. And then here's the sort of the vocabulary I'm going to try to stick to. I'm going to slip many times, but shoot me when I do. So we're going to have publishers who produce content. They're going to produce the content, and in the case of private content, they will also do key management. So the publishers are going to be put in charge of managing keys to give people access to content. Now the clients, their job is, well, these mongers, all they want to do is read content. They don't want to pay for it, but they're going to read and verify content. And for the purposes of this talk, we're assuming there's some kind of relationship where they know the publisher's public key. We happen to use self-certifying path names to get that done. But for right now, we'll just assume that clients are able to get some kind of toehold into the publisher's public key. Now, untrusted servers are actually going to be replicating the content. Again, we trust them for nothing. If they do a good job, great. If not, they can deny us service if we don't have some kind of Byzantine agreement. Now, all of this is happening at the file system level. In the commercial world, CDNs are sort of synonymous with web content. So what we're talking about today is doing these kind of techniques, but in the file system world. So we're actually going to protect not just web pages, but entire directory trees. And that means it's going to include all the metadata, all the data, everything in the file system at the block level. So the contributions I'll talk today are here. This also serves as the outline of my talk. First, I'll talk about a slightly dated file system I've worked on, the SFS read-only file system. Its job is to provide authenticated content distribution, again using untrusted servers, but it's specifically tailored to public content. So things like open source software, hierarchies of certificates, for instance. The second part of the talk will discuss an extension to SFS read-only to handle access control. So we're going to start off with this authentic content, but we're going to add access control, decentralized access control. So again, we're not going to trust the untrusted servers for even mediating access to content. And that's sort of a solved problem of how to actually do that. But what I'm going to talk about is how to do it efficiently. So I'll talk about how to do very efficient eviction. So if you want to prevent someone from getting access to future content, how can we do that efficiently? So I'll talk about how the semantics of lazy revocation takes care of that. Then I'll also talk about how key regression will help us minimize the amount of key material that clients need to actually download from publishers. Because we still want to make sure that publishers can control access, so the publisher is going to be the one actually having to distribute keys. And all of this is actually implemented. At the end, I'll give some performance measurements to justify why all these efficient operations are truly efficient. And it works on all your favorite operating systems except the one written here. But I actually want to have it work in Windows, but it's rather difficult converting the system calls to the Windows world.
So you're saying it works on all of our favorite operating.
All of our favorite operating systems. And if you run VMware like I do, you can then run it in Windows. Okay. So onwards to SFS read-only. So I should preface this with SFS read-only is actually a misnomer. The read-only is really only from the perspective of the client, because the content actually does change. The publisher can update the content and push updates out. So you just have to remember this is all sort of, the better name would have been SFS single writer, many reader content, but it just doesn't roll off the tongue. So we stuck with SFS read-only. So these are the challenges that we had to face for designing and building SFS read-only. Well, right off the bat, the main goal was, well, how do we provide authenticated content when it's read-only? And that's not too hard. You could just sign it, right? So what we were more concerned with was doing that efficiently. So I'll talk about how to provide incremental updates so that the publisher doesn't have to do an inordinate amount of work if there's only a small change to the content. Similarly, on the client side, again, we're in the file system world, so we've got directory trees. If you are a client and you just access a single file in this huge directory tree, we don't want to have to force you to verify a digital signature, for instance, on all the content. So I'll talk about how to authenticate partial downloads in an incremental manner. And then finally, our untrusted servers, I want to make sure that they're so fast that whatever kind of throughput you give it, whatever kind of network it's connected to, it should just be able to saturate the network. So no cryptography should get in the way on these untrusted servers. All right. So here's an example of how the content distribution used to work for the Red Hat operating system. So this, back in the day, Red Hat had this lovely web page. I think I got it from the archive, actually. And on the web page, they listed several hundred mirrors. You would visit one of these mirrors, and you would download all the Red Hat packages to install the operating system. And it actually worked in terms of authenticity because they digitally signed each individual software package. So you as a company, you could actually visit, mrhanky.bizserv.com. You could download this strange software, but because you're able to verify the digital signature, you can have some assurance that you're actually getting the real deal. So what was great about the signed software packages was you got this authenticated content. But that's not sort of the complete solution. And so where SFS read-only comes in is how to handle the case as content is changing and how do we do this efficiently. So for instance, one thing we need is revocation. So if a bug comes up, if there's a security hole that appears in a software package, we want to make sure that users don't continue to install that package. So our solution is pretty straightforward. We just have a very short essentially expiration time. That's not too tricky to do. The tricky part is, again, well, how do you do that efficiently? So if we have very short expiration times on signed software packages, how can we have incremental updates? If I have a 1 gigabyte software package and I make a 1 byte change, I want to make sure that I don't have to pay a huge cost. That cost should be somehow relative to that, just the size of the amount of content you're changing. And then finally, here, again, we're talking in the file system. So I'm talking about not just integrity of individual files or individual blocks. I'm talking about the integrity of an entire collection. So I want to know if a file is missing, if a file has been rearranged, if it's been renamed. I want to know that the content is exactly as the publisher intended it to be presented in its context. So to motivate that, here's an example of all the software packages available on my Debian server. I happen to be using the testing and unstable branch. But my question would be, if you've picked a mirror that's putting out all these software packages, each software package is individually signed. Well, even if they're individually signed, how do you know if what you're downloading, what you're installing on your system has integrity as a whole? Is one of these software packages removed? Is one reverted to a previous version that had a security hole? Right now, the dependency information is not going to guarantee any kind of security. It's only going to guarantee that it runs. So what SFS read-only is going to address is how to get this integrity of entire collections.
Does it even guarantee it? I mean, it's just guarantees that I've got some signed at some point.
Right. So, well, okay, best case it runs. Might not run. I haven't had too many issues, but yeah, you've identified even more trickiness. For instance, each of these software packages is signed by a different individual, and they have no mutual agreement, no agreement between each other. So it gets tricky to do.
At this point, I've got to ask, why is this required that the president has to present the word and sign manifest?
Okay, so again, I'm talking about tree kind of data. I don't want to have to verify an entire manifest. For instance, if I'm VeriSign, I don't know how many certificates they mint a year, but probably millions at least, I would imagine. I don't want to even have to re-sign a manifest every day, for instance. I want to be able to afford to do this very periodic with very short expiration times. So any kind of signature is going to have to be, I'm going to rely on tree-based schemes to do the signatures. Okay. So here's an architectural picture of how the system works, how I implemented it. On the publisher side, and we have a secure area offline, and we have a database generation program aptly named SFS RODB that everyone seems to hate the name. It takes as input two things, an origin file system. So again, this is your hierarchy of content. It could be your open source software. It could be unsigned X509 certificates, whatever you'd like to put out. And it also takes as input a secret signing key. So what the database program is going to do, it's going to take that content and then produce a signed collection of content and push it out onto an untrusted server. Now this collection actually looks very much like a disk image because everything's going to be blockitized as if it were blocks on a disk, but then each block is going to be authenticated and then formed into an authentication tree, and then that root of the tree is going to be signed. I'll talk about the tree in a moment. But anyhow, all that content gets pushed out onto one untrusted server, and at that point, any other untrusted server can just further replicate the content. So from some of the smiles, I get the sense that this has been done here or something like that. But here, the client, if the client wishes to access the content, it locates one of these untrusted servers and pulls the content down. So the client, what it has to do is two things. First of all, it's got to synthesize these requests. So it's a file system, right? So it's going to be getting requests from your web browser, your software package management tool, and it's got to sort of desugar those into from the file system request into block requests. So the black line from an untrusted server to a client is a very simple protocol of here's a name of a block, give me the block back. And so the two things it does is it synthesizes up into a file system, and at the same time, it's going to be verifying a digital signature and incrementally verifying any content you get. And the semantics it's trying to guarantee is that the client will never accept unauthentic content. The worst an untrusted network could do is delay access to content. Maybe this is a good point to mention. The reason why I implemented this as a file system, well, it's going to give any existing tool the ability to just inherit the kind of semantics I get. So again, any existing software tool that you use will be able to make sure that it only receives authentic content. At worst, it'll be delayed. And furthermore, it tends to be, I found in my experience, if you can build this stuff into a file system, you can build it just about anywhere. The file system tends to really stress test things. And the techniques I talk about actually work very well in other arenas. Anything tree-like, XML structures, databases, and such. The kind of techniques I'll talk about generalize very well. One of those techniques, which is becoming very popular these days, is using a Merkle hash tree to provide authenticity. So I'm not ashamed to use, a good cryptographic structure, so I'm going to go ahead and use it. But the basic idea is that it's very easy to prove whether an element is a member without having to have a very long proof, basically. So logarithmic in the size of the content. Now, so the way the Merkle hash tree works, did I say trash? Merkle hash tree works is that it takes your content at the leaves of the tree and then uses a cryptographic hash to hash it upwards, using this cryptographic hash upwards. And at a high level, what it's going to do is it's going to make sure no one can modify the content, switch around the content. If they were to somehow damage the integrity, they would also be able to, for instance, invert one of these functions. But the nice thing is, the Merkle hash tree matches almost perfectly the typical structure of a file system, because the way we access file systems is in a depth-first manner. We always start at the root, and then we walk downwards. So we'll find that the Merkle hash tree is just going to be perfect for getting this incremental integrity verification. So here's how I map the Merkle hash tree onto my file system. So in the database generation program, it actually does a depth-first search. But when it reaches terminal data, which is always going to be terminal data within a file, it hashes it. And then we're going to do what is pretty standard these days and generate a content hash. So for instance, that first piece of data, it gets hashed, and it produces a content hash. And the content hash is going to serve two purposes. It names the data so that you can find it later on. It's going to be its probabilistically unique name. And it's also going to help us provide integrity. So it produces a whole tree hashing upwards until we finally get to, say, the root directory / or C:, I guess, here. And we're going at the top. We've hashed all the way up, but at the top, then we'll produce a digital signature. And that's how we're going to get that toehold into the authenticity. So the nice thing is, for this entire tree structure, we have to pay for only one digital signature, but then we pay for hashing up here throughout the tree. Now on the client side, to access the content, you of course go in the opposite direction. So if you're asking to read the directory / and you want to get its content, well, you ask one of the untrusted servers for hash of inode, because that's the name of the inode, for instance. So this inode structure comes back, and the client then rehashes the content to verify that the content hash is correct, and that's how we get that authenticity. Because we've already believed in the authenticity of the root inode, the root file handle there, because it was digitally signed. But the nice thing is, the file system is just designed to walk Merkle hash trees. So as we walk down through accessing data, we're going to incrementally continue to verify the Merkle hash tree structure. So here's an example of how it works if you're a client and you want to connect to an untrusted server. After you locate one of these lovely servers, you ask for some initial information. So the way SFS works, in the SFS model, everything's auto-mounted. So by accessing shome sfs.sf.net, fs.net, it's going to return back the signed root file handle, some basic high-level mount information. So at that point, the client verifies the signature on the root file handle, and that's again how it gets the toehold into the authenticity of the Merkle hash tree. Now the job of the client is again to desugar all these file system requests into block level requests, kind of like how you would access a disk. You give it an address on the disk and the content comes back. So here, instead of using a disk address, we ask for a content hash. The server responds with the associated content. So here the root inode happens to come back. On the client side, we rehash it, verify that it matches the name, the original content hash. Now we've been guaranteed that it's authentic. And that process just continues, synthesizing file system requests into block requests. So, right, but what I'm worried more about is sort of the critical path, because the server has many clients. So the online is about the server. So the server is doing no online cryptography. All the cryptography, the digital signature, the actual production of the Merkle hash tree has been done offline. So this doesn't have to be done by any of our untrusted servers, which gives us two things. Performance, we're going to be very efficient just because there's no CPU cost on the server, really. The biggest cost is going to be looking up in a database, actually, and network latencies. And the second thing is you don't have to trust the server with any key material, which turns out to be pretty nice because there's nothing to break in to do. A person could break into one of these servers, but the best you could do, or worst you could do, is prevent someone from getting access to content. So here's how it's actually implemented. I'm using the SFS file system toolkit. I happen to be using a SHA-1 based Merkle hash tree. Now, if you're up with the literature, maybe I should be using SHA-256, but for this prototype, I'm not too worried. I happen to be using the Rabin-Williams signature to sign the root of the handle. Hi, Dan. Okay. At a very gross level, if you're not a cryptographer, you can think of it in terms of RSA signatures. But for the cryptographers, I'm sorry for being gross. But it had some very nice intellectual property semantics. Again, the word semantics. I love that word. Okay. On the block servers. What?
Yeah, this was done in 99.
Hmm?
This was done in 99.
RSA has nice eyepieces.
Yeah, it now does. Yep. So the design's pretty old. In fact, some of this came out of my master's thesis, which, well, I completed that in '99. So, but then we sort of took the techniques further, and the master's thesis wasn't exactly a very polished thing. But anyhow, sign of the times. But so on our block server side, the way the block server is implemented is we use the Berkeley DB SleepyCat database. So I don't worry about how to translate from these content hashes to content. I just let the database do the work. Actually, Franz, I think, burned through probably 2 or 3 graduate students trying to implement B+ trees. So we're just using the B tree inside SleepyCat. And that's how the server is going to know when it's given the content hash which data to return. Now, it turns out by using this sort of database-like structure along with a Merkle hash tree, it's just trivial to get incremental updates. So let's say you're a publisher and you have a change to make. So maybe you add a file or you push out a new file. Well, how do you as a client make sure you get the content but in an incremental fashion? Well, first of all, you have to download the new root file handle. That has to change because by definition of the Merkle hash tree, we're hashing upwards and it's got to change. So we ask for that content. Now, as the client, we start to rewalk the whole tree. But when we encounter a content hash that we've already seen, we say, aha, we don't need to traverse that tree any further because we know there could be no further changes down the line. Otherwise, the hashes would have all changed. So that's how we're going to get the incremental updates. Now, the block server actually influenced one of the CORD projects, the cooperative file system. That's how they got their initial block store. On the client side, the client is actually the most interesting part, the most sophisticated part. So its job is, again, it has to do the transparent integrity checking. So all this gobbledygook down here is the NFS loopback server provided by the SFS toolkit. But then all I had to do was implement something up in user space, so I never, well, seldom had to reboot my machine. But again, it's going to be synthesizing from what is step 8 up there is sort of the I/O interface where it's got basically one remote procedure call. Give me the content hash, and then the content comes back. And then line number 7 is going to consist of about 15, I believe, NFS remote procedure calls where it's translating all these blocks into, reading from a file, looking up in a directory and such. Okay. All right. So now we're going to move on to the case of access-controlled content for private content. I call the system chefs, and I don't really have a good reason for calling it chefs, but go ahead.
I'm sorry, for the last part, so this file system, did you do any performance benchmark?
Yes, I do. At the third part of the talk will be all the performance stuff. So actually, the performance is, yeah, I won't skip that. All right, but moving on to chefs. So here I have a brief timeline of how things evolved, and I'm getting really scared with all these smiles, like something's going wrong. But okay, so actually that's a what? Okay, or start weeping. Yeah. Okay. Super. Okay. So Dave Mazieres had worked on his sort of general purpose read-write file system. It was actually much more than a file system. But in around 99, 2000, we started looking around and sort of looking for common cases. Where could we optimize? And so we said, there's this web thing. Tends to have mostly read-only content. So we thought, seems like it'd be a reasonable idea to try to provide security for just that kind of content. So that's where SFS read-only came from. Now, in more recent times, I've been working on an independent project providing access control in the exact same model where, again, we have these untrusted servers. So the basic idea is that in Chefs, clients who have the proper key will be able to get access to content. So again, it's straightforward. You just encrypt the content for confidentiality before pushing it out on your untrusted CDN. And what the problem I'll be addressing is, well, how can we do this efficiently again? So I'm going to be talking mainly about how to avoid key distribution, because in cryptography, if your problem boils down to key distribution, you sort of run away. It's typically a hard problem. But yeah, again, chefs, though, is this name. I didn't have a good expansion, but if you sort of say chefs, it's supposed to have this sort of air of secrecy. Or as one colleague called it, CHEFS. But, all right. So returning to the plight of our graduate student, in addition to having this wonderful open source software, now she's got a private blog. The blog happens to contain quite a bit of photography, so we're talking about a lot of content that usually requires high throughput. So she's going to take advantage of a content distribution network, but she wants to make sure that it can have access control. So only the folks with the decryption key should be able to get access to the content. So there are a couple straightforward ways you might try to do this without building it yourself. The first thing I would try to do would be, well, SSL is out there. It's pretty much accepted. So why don't we just have proxy SSL servers all over the place? And that's a reasonable solution in trusted storage. But it turns out that it doesn't work in the model of untrusted storage because SSL is specifically designed so that you will not be able to replicate confidential content on untrusted servers. In fact, if you do have an SSL replica, you'll usually find that the key material is also going to be replicated on each replica. So the approach we take, the general idea is to do encryption of the content first. The simplest way to do this, again, if you didn't want to build yourself a file system, was just take your favorite tool like PGP or GPG and encrypt the content, and then make that content pushed out onto this content distribution network. If a user wants to get access to the content, they could do one of two things. If it happens to be protected with symmetric cryptography, they need to get the symmetric key. If it's protected with public key cryptography, then the publisher needs to know the public key of each user and encrypt it into each of their public keys. So there are a couple drawbacks to that that Chefs tries to address. First of all, the transparency issue. The nice thing about the file system abstraction is that you just get these, you get the confidentiality without having to sort of think about it. So if I'm going to compile some software that I've purchased and it's being distributed using Chefs, I don't have to hand decrypt each file, for instance, or open up a tarball and decrypt it. All I have to type is make, and it's just transparent. It works through the file system. Second, if you were to say just do the naive scheme of encrypting in each user's public key, well, that works perfectly fine for small groups of users. The trouble is that's going to scale, though, linearly in the number of clients. And so in my model, I'm trying to address the case of many readers, and so I can't use a scheme where the ciphertext is going to scale linearly with the number of folks having access to the content. And finally, we get back to the old problem of how do we efficiently handle incremental updates. Again, if I change 1 byte of the file, I want to make sure that we're going to have efficient distribution of that amount of content. And also, the publisher shouldn't have to pay a huge computational cost to push out the content. So for instance, let's say you've got a gigabyte of content and you modify one photograph. We're not going to be able to afford to push out an entire re-encrypted 1 gigabyte. So we have to come up with a different solution to handle that efficiently.
This may be a semantic question.
Okay.
When you talk about ciphertext scaling linearly the number of clients, the public key approach would usually be to create a single content key with that and encrypt just the key. So only a small thing.
Right. So one of my goals here, though, has been trying to keep everything constant. It'd be interesting to take a look at the constant factors. I'm not sure how well that would scale. Like, what would happen if, let's see, you change the key? Would that mean you'd have to re-encrypt each one of these master keys or lockboxes for every user if you change the key that encrypted the file? Yeah. Oh, okay. But sort of, I originally implemented a lot of this in the broadcast encryption model, and actually it was the last time I programmed in Java, I think. But I found it was just sort of too hard to think about everything, trying to do everything at once with broadcast encryption or non-interactive key distribution. So instead, I'm going to talk about just some very simple constructions to give very clear semantics. All right. So the approach of encrypting for confidentiality is not new on its own. In fact, the most interesting project I saw was David Reed in his Swallow object store in 1981. Actually, it was a really great design where they were encrypting objects, putting it into an untrusted store, and they started to encounter some of the same problems. Unfortunately, for political reasons, basically, it never actually came to be. But so here you'll get to see some benchmarks of a system in that manner. So one of the problems I run into is, again, handling key distribution. So I'll talk about how lazy revocation is going to help us efficiently evict members from getting access to future content. Then after that, I'll talk about key regression as a technique to allow remaining members to get efficient key distribution, so that we'll explore workloads where a user will not have to fetch keys often from a publisher. Because again, our publisher is on a very low bandwidth connection, possibly even zero bandwidth if the publisher is offline. Okay, so let's try to plow through this slide. So here's some sort of necessary framework to understand how the implementation actually exists. So the way Chefs encrypts content is each piece of content, it's a block, and it's going to be encrypted for confidentiality using a unique content key. So we have a blue content key for each block, randomly selected. Now, carried along with each block of encrypted content is a lockbox. So that lockbox, again, contains a unique key, which is itself sealed with a group key. So here we have the red group key. So for a client to get access to content, what they have to do is fetch the group key, and the group key is going to protect an entire tree of content in a sort of all or nothing fashion. Either you're going to have access to all the content in the directory tree or none of the content. If you'd like to have a different access control policy, then again, I say simplify, just have two databases, and you could link them using symlinks. But anyhow, so the client will get access to the group key, which can then open up the lockbox. You open up the lockbox, you get the content key, and at that point you can get access to the content. So the reason I have this machinery here, multiple kinds of keys, well, first of all, it turns out that a lot of content sort of has access control locality. In fact, on a typical Unix machine, you'll find maybe 30, 35 equivalence classes of access control policies. So what we find is that if you have access to one file in a directory, it's very likely you have access to another file. So it makes sense just to protect it all with a single key rather than...
What's the rest of hard links?
So the way the symbolic links work is using self-certifying path names. So it's other work by other people, but the basic idea is that you point to somebody else's directory tree in an authentic fashion. Hard links, here it's going to be duplicating content. So we don't get, for instance, convergent encryption properties of coalescing data. They'll be considered separate data, I believe.
So it's not a link anymore.
I'm sorry?
It is not a hard link anymore.
It is not a hard link.
With the hard link, you don't
Yeah, so the semantics are going to be slightly different. In fact, yeah, they're going to be...
It's not writable data, but you can't tell the difference. It's not readable, so you can't tell the difference. Well, you wouldn't see in a single instance, but over time, you hard link, you notice both change. But there's necessity to not be mentioned. But the point is that you can't write this process.
Yeah. Unfortunately, there are no hard links for directories. That would really complicate things. But it turns out, yeah, actually, some differences would be in if you try to rename a file. Actually, some strange things come up. If you want to preserve file handles and such, it can become difficult when you're using content hashes. But anyhow, so the group key is used again to coalesce, so we have all these files protected under one policy. And then the reason why I'm using individual content keys is just so I can keep the entropy sort of relative to the amount of content I'm protecting. Because sort of in the game of cryptography, it's all sort of about risk management. So the more you use the key, the more information is going to leak. So I'm just trying to, I'm not getting rid of the leakage, but I'm trying to at least minimize it by using randomized content keys. Now, actually, one benefit you get out of using one of these group keys is that as a publisher, if you add content to the system, there's no key distribution required because the client already has the group key, and all it has to do is fetch the lockbox. All right. So the architectural overview of Chefs is extremely similar to SFS read-only, with the introduction of just another group key for providing the confidentiality of content. Now, the ugly part is that we've sort of added this key distribution line, this ghastly red line, where now on our critical path, we have the client who needs to fetch keys from a publisher. So what I'll talk about now is basically how we avoid using this. I want to use this as seldom as possible. Okay. So a straightforward approach to evicting somebody from access to content would be, well, you kick somebody out of the group, so let's just re-encrypt all the content after the eviction. And then we distribute a new version of a shared symmetric group key to our remaining clients. But that's not going to work for us on our low bandwidth connection. Even if we could do the recomputation, we wouldn't be able to distribute the content. And it turns out in the model of untrusted storage, actually, the re-encryption is not even necessary. The reason for that is in untrusted storage, a client could have actually cached all the plain text already. So it's sort of, why bother re-encrypting if they could have accessed the content anyway? As a publisher, we don't control the untrusted server. We cannot stop them from serving old content. We could try, but we cannot guarantee that they will stop serving old content. So the approach we take is to use the lazy revocation. So what lazy revocation guarantees is that an evicted member will not get access to future content. So what happens after an eviction is the publisher generates a new group key for future updates to content. And then that new group key is made available on demand to any client who needs it to get access to content. And what's nice here is, again, it matches the semantics of untrusted storage. Because lazy revocation is going to enable a person, it's not going to prevent you from getting access to old content. In untrusted storage, we can do nothing about old content. Once it's out there, and we have to assume the clients who had access have already downloaded it. There are extensions to lazy revocation if you'd like slightly stronger guarantees, but we can talk about that later if you have questions. So one of the problems, though, if you do use lazy revocation, is that you get into this problem where you're going to end up with fragmented keys. You're going to end up with many, many versions of the group key protecting content. So in this example, we have a collection of bakers, and they have these encrypted bread recipes. So we begin with the Paul Levon, and it's protected with group key version 1. But oh my gosh, suddenly comes along, this baker who starts baking, soft crustless bread made of only, white refined flour. Oh, heavens to Betsy. So we have to revoke that guy. And what we do is we wind the key forward, we take the group key, and we go to version 2. And what we find is that as we sort of do this, evicting people from the group and producing new content, we're going to have this fragmentation of keys. So a client who, for instance, has legitimate access to the Ciabatta, which is protected with group key version 4, should actually have access to all the old content as well, but now they have to download 4 times as many keys. So we want to coalesce all those group keys actually into one version. So the way I do that is using key regression. So what key regression is going to do is it's going to guarantee that a client will be able to get access to old content, but they will not be able to get access to future content. But at the same time, they're going to be having to download as few keys as possible. And the way I do that is that a client, for instance, who has today's key can unwind that key backwards in time to derive old versions of the group key. And then that, in turn, gives the client access to old content. But at the same time, the publisher is the only one who can wind the key forward in time to produce new keys. Otherwise, you wouldn't be able to evict people. And what's great about this is that we'll find workloads where a low bandwidth publisher can then actually exist. A low bandwidth publisher can actually control access then. So for example, let's say if you're a client and you want to search through a file system for some particular kind of content. Well, the client's going to be performing the search, not the untrusted server, because, well, even if the server could do the search, we're not going to be able to trust its answer. So the client will have to do 2 things. It's going to have to download all of the encrypted content, and then it's going to have to download all the keys protecting that content. So in the case of key regression, it's pretty obvious that if you're in that workload, you only have to download a single key. Instead of, for instance, in one scenario where we took a look at Salon.com, we contacted the Salon.com folks and looked at their financial reports, and we determined they had about 60,000 membership events a year. It's a reasonable number. And so there you can imagine, you have your choice of downloading 60,000 keys if you want to look through all the content, or downloading 1 key. So you're going to get this throughput trade-off for the publisher. At least now, a publisher on a low bandwidth or near zero bandwidth connection can at least exist.
But you can't do what a lot of publishers do, which is migrate their content to an archive that requires special privileges.
Right. So again, we're going to be in the model of untrusted storage. So we're not going to be able to prevent someone from getting access to past content.
Well, that's just a question of untrusted storage, right?
Mm-hmm.
If I have a subscription, or
Mm-hmm.
if I have a subscription service, I use these untrusted servers,
Mm-hmm.
I may still want to say, you get access, you subscribe now, you get access to this year's content.
Mm-hmm.
If you want archive access, we sell you the content.
Actually, that's a good point. So Actually, I won't be talking. There are a couple extensions to key regression. I'll talk about one, but there's another one I call windowing, where you can limit how far back in time somebody can unwind a key on a per member basis. Turns out to be pretty tricky, though, and I think there's some better approaches in the realm of non-interactive key distribution to handle the case where you want to limit how far back in time someone can go. Yeah. Okay. Well, but it's tricky to do. But maybe if I plod through the key regression, then you can begin to appreciate why adding these extensions can get pretty tricky. All right. So here's sort of the simplest way to describe a construction of key regression. But sort of the notion of security, I'm not going to talk about the theoretical notion. But here, the basic idea is that clients can unwind keys, only the clients, not non-members, and only the publisher should be able to wind the key forward in time. So if you have version I+1 as a client, you can very easily get version I. If you have version I of the key as a publisher, you can very easily get the next one. Now, sort of at a meta level, you can try to believe sort of in the ideal case, the sequence of keys produced by key regression should sort of behave in an indistinguishable fashion from a randomly selected set of keys. So that's our ideal goal. That's what the best case we could have. So here's the simplest way to use key regression. I'm going to ignore for a moment the winding algorithm, and I'm going to basically implement a hash chain here. So as an owner, what you do is you initially generate your final key, what you think is going to be the last key you would ever distribute, version T-1. And then you compute all the earlier keys by unwinding backwards. So we just go backwards until we arrive at a point where you say, okay, we've gone far enough. Let's just settle on this key version 0, and we make that available to our clients. Now, a client who comes along at a later time I, well, this client would like to get access to some old content protected with a different key version J. So again, the client just has to unwind the key backwards in time until it arrives at version J, so key KJ. And at that point, the client can then decrypt the content to get access. So that's, again, that was an example of very much like a hash function. So here in the implementation, actually, I do use a hash function. We're going to produce a group key sequence from this hash chain. I happen to use SHA-1. Again, maybe SHA-256 is a better idea. Now, in theory, actually, there's a little bit more machinery if you want to get some more provable statements out of it. It's actually a better idea to use a pseudorandom function family in the random oracle model. Or if you're using block ciphers, you can tend to avoid the random oracle model as well. And I'm sort of, again, this is just like the Merkle hash tree. I'm sort of not embarrassed to use the hash chain. It actually turns up quite often in other literature. Lamport and the one-time passwords, or Ross Anderson and folks with their forward secure encryption. It's a very good technique. Okay, so getting on to one extension though. One extension would be, well, that's great, I can do this hash chain, but what you find in almost all applications that use hash chains is, well, you've got a finite number of keys. You've sort of picked ahead of time how many keys you can support. So now I'll talk about how we can use a trapdoor pseudorandom permutation to grow a key sequence. So we're going to use our favorite function, the RSA exponentiation. So if you're a publisher and you'd like to grow the sequence forward, what do? Well, you exponentiate to the secret exponent d mod n to go forward in time. So that's an operation that would be difficult for anyone who doesn't know d to do. Now, as a client, if you want to unwind the key, you then use the public exponent, the public RSA exponent. So you're going to exponentiate to e mod n to go backwards in time. And so what we're doing here, we're sort of using RSA in a strange way. This is not sort of the traditional way. But the basic idea is that we're relying on there's going to be no short cycle in doing this operation. It turns out if you can find a cycle, then you can actually factor. We're relying sort of on that, I believe, phi of n has at least one large factor in it. But it's actually doable. You can actually get these long chains. Now, RSA tends to be a sort of heavy-weighted operation. So if you are concerned about that trade-off, well, you can actually combine hash chains into any sort of directed acyclic graph you prefer. So here we have RSA going on upstairs so we can dynamically grow things. And then downstairs, we're just attaching hash chains. This is similar to some techniques, and actually maybe one of the good things that came out of key escrow in the 80s. All right. So in terms of the implementation, the untrusted servers remain unmodified. Actually, they don't even realize they're serving encrypted content. They're just opaque block stores. But on the publisher side, we had to come up with a more sophisticated algorithm for doing the incremental updates. And that resulted mainly from the lazy revocation and the fact that we have random content keys. Because in the case of SFS read-only, we're actually able to cheat in terms of doing incremental updates. If we updated content, we just said, throw out the old database, let's generate a new one. Because we'd always end up with the same database if the content didn't change. But here, since we have random content keys, we can't do that simple trick. So we have to be slightly more careful at making sure that we lazily re-encrypt, and we only re-encrypt things that actually changed. Now, the key regression was implemented using SHA-1, and we have this out-of-band channel for getting the keys. I glossed over sort of a fourth part of key regression, where it turns out you actually want to have an extra step. What key regression actually does in the constructions I presented was it produces unpredictable keys, but they're not necessarily pseudo-random yet. So there's one extra step if you want to actually get pseudo-random keys. Okay, so somebody asked about performance, right? So I'll actually get into some performance here. And that was actually the main motivating factor for this work, making sure that everything would run efficiently. So first of all, I wanted to make sure that as a publisher, again, you could exist on a very low bandwidth connection and yet still have a large audience being able to download content at high throughput. Now, each one of these individual untrusted servers needs to be able to support many simultaneous clients. As I pointed out before, they're not doing any cryptographic operations, so we're basically going to be as fast as TCP and the number of file descriptors we have. Now, on the client side, the clients want to make sure that they have reasonable latency. I want to make sure that, say, relative to other file systems, they won't have to wait much longer, or maybe even not at all. And in the case of key regression, we find that Chefs performs equally to SFS read-only, except, of course, for the downloading of keys. So if you have a case where you can compress downloading 60,000 keys down to one, it's going to be obvious the amount of key material you have to download is much less. Okay, so here's one of the benchmarks I used. So here's sort of an application level benchmark. On the left-hand side, I'm installing Apache on my Debian machine, and I'm downloading the Debian packages, which consist of 3 software packages from a server using these 3 file systems. And the important thing to note is that it's just a very level bar chart. We find that the cost of verifying the Merkle hash tree, verifying the digital signature is extremely small. You can't even tell that you're paying for cryptography here because we have an I/O and CPU workload going on. Similarly, adding the confidentiality adds no discernible cost in terms of latency to the client. So I tried another benchmark, the Emacs compilation benchmark. And if you ever see Emacs in a benchmark, it's probably an SFS paper. But it's difficult to find workloads that work for read-only kind of content. So here I have a server that has all the Emacs source code. Exactly. So the object code is going to a local hard drive, but all the source code is coming down. Yeah, because this actually the test only works with where you can do out of directory builds, which is nice. So here we actually do see a slight cost. You can begin to see the cost of verifying the integrity, and there's a slight cost for the confidentiality. Now it actually turns out if you analyze where each second is going, it turns out most of the time is just spent in the basic implementation. If you turn off the verification, the bar doesn't go down much it's simply because it's user level code, and we've got this context switching going on. There's quite a bit of extra latency that we pay for the portability. I think that's probably right because in the micro benchmarks it confirms. I'm sorry?
Or just the scale smaller on the left, so you can actually see the percent difference on the left. I mean,
Well, you'll find, in the next slide I'll show you the micro benchmarks, and why don't we go to that? So in the large file benchmark, what I'm doing is I'm downloading a 40 megabyte file. At the time, that was a big file. I guess gigabytes are the vogue thing today. But I'm reading that file in 8 kilobyte chunks. And what we see is that, again, the cost of integrity is you can actually see the cost of integrity now because I removed the CPU from the client. In the Apache and in the Emacs compilation, we were able to overlap some CPU and I/O on the client, so it would hide the cost of cryptography. But here, the cost is becoming more evident. Now, it actually turns out that if you take SFS read-only and you add confidentiality, you actually get slightly better throughput, which is kind of counterintuitive. But I've now learned to attribute this to just poor block alignment in SFS read-only. Sort of the goal of SFS read-only was I was trying to go for these 8 kilobyte blocks, but it turns out there was just a little bit off. In fact, the Sleepycat database doesn't do so well when you have data that's just a couple bytes over a power of 2 content. And so I found actually by adding, because I had to pad the content when I do confidentiality, everything has to be done in a certain number of blocks. It turns out I actually get better throughput. But that's sort of a side note. The big picture is, though, that, again, the cost is rather small compared to just downloading content through a traditional file system. I don't have them handy at the moment. So for the large file, well, there's no CPU on the server.
Because you moved all the CPU intensive stuff to
Yeah.
the clock, right? I think that's some.
Yeah. Actually, I'd have to look it up myself. I see the papers right there. I can't remember off the top of my head what the percent was. But we could talk afterwards. I can look it up.
And for the smaller files, did you find that again your CPU limited there? I would imagine you'd have to do some encryption per file. And if you have a whole bunch of little wee ones, that could dominate.
Yeah, actually, I think for the encryption, we were much more CPU limited. It was getting upwards of something like 80% of the CPU, I believe. Yeah. But sort of our main goal was, though, to keep the untrusted infrastructure scalable. I know clients are not free, but they're more free than putting the cost on the inner nodes of our system. Okay, but for the small file benchmark, that's supposed, well, this is from the LFS benchmarks, right? And it's supposed to represent reading 1,000 1 kilobyte files, which is typical of, say, reading email. So again, we see that the cost of integrity is minimal. The cost of confidentiality comes up actually quite a bit more, though. But fortunately, it's all just about 1 second. Now, to show that the servers scale, that was a little tricky to do, and I didn't have a million clients at my disposal, so I had to do a partial simulation. So what I did was I went back to the Emacs compilation example, and I took a trace of all the asynchronous RPCs, at least all the arguments going across from my client to the server, and then I replayed it. So I took a whole trace and then replayed it simultaneously. So I started playing it back once, and then I tried replaying back twice at a time, and so on and so forth. So I was able to simulate a horde of clients going to one of these servers. And we were able to quickly ramp up to whatever the network could provide. And the basic bottleneck was just the TCP on the server, just confirming that the servers have no real cost besides TCP and looking up in databases. We got up to about 300, I think, until we discovered a bug in NetBSD that caused the kernel to reboot. But then once we tried again in OpenBSD, and I think we were able to get something like something along the lines of 800 per second, still being fair to all the users.
So what were these clients doing? Like enumerating the whole file system to the server, or just reading one or two files?
No, so I literally took the trace of the exact ordering of RPCs as you compile Emacs. So I took the exact RPC traffic and then replayed it.
How many files are involved?
I believe about 300, mostly small files. Mm-hmm.
So if there's 300, the file system cache for the server is probably 70% of that, right?
Yeah, so I do have metrics of the caching, disabling the cache and such. Trying to recall. I can't recall off the top of my head the caching measurements, but the basic idea was, though, look, the cost of adding the extra integrity came at no cost. Oops. Okay, so to wrap up, there's quite a bit of related work in the area. In the secure file system arena, I talked today about how to do the single writer, many reader case. But there's actually quite a lot of work in multi-writer. So for instance, David Maziers is working on how do you do consistency when you have multiple writers on untrusted storage. turns out to have much different problems than in the case where you have a single publisher. In the case of content distribution networks, the closest thing to this work would probably be this sort of clever hack by Chris Loss called SSL splitting. And there what he did was he says, okay, we're going to have untrusted SSL proxies. And if you recall earlier in the talk, I mentioned you can't do that. SSL won't let you have untrusted servers as proxies. But then Chris figured out, well, that's only half true. It turns out if all you care about is integrity, you can have replicated SSL servers. So he had this clever hack that the main goal was to be deployable. You didn't have to change any of the client software. And you were not able to guarantee confidential content. The proxies would be able to get access to the plaintext, but you would still get end-to-end authenticity. In the realm of cryptography, again, I mentioned forward secure encryption. Key regression is actually doing the exact opposite of forward secure encryption. So the goal of forward secure encryption, for instance, well, by example, let's say you have a server that has some kind of private key material protecting communication. If an adversary comes along and breaks in, you want to make sure that adversary cannot get access to past communication. So you make sure you cannot get access to the old keys. But at the same time, you need to be able to generate new keys so the adversary will be able to derive future keys. Now, the reason why it makes sense to do the exact opposite is because in this system, we're in the model of untrusted storage. First of all, we're not dealing with communication, we're dealing with storage. So the job of our system is to give you access to old data. We want permanency. So that's why it makes sense to allow people to be able to unwind the key, but prevent them from winding the key forward. And so what I talked about today were selected pieces from 4 papers, mainly in the realm of untrusted file systems, or file systems built on untrusted storage. In a slightly larger context, it relates to some work I've done as a general developer for the SFS project, and then some earlier work in how to revoke email when it's distributed on an untrusted network. I didn't get a chance to talk about some sort of fun, lighthearted work I did in web authentication. So I spent a couple years analyzing, okay, if I log into my bank, I type in my username and password, why is it when I click on a link later on, I don't have to type my password again? How does it know who I am? How does it keep me authenticated? And so we analyzed a bunch of these schemes, typically using session IDs and cookies, and we found that most schemes actually did not work so well. So, for instance, in the case of the Wall Street Journal, we were able to reverse engineer their message authentication code system, and we determined it was actually weaker than using plaintext passwords, which is quite a feat. But if you're interested, I can talk to you about that later in one-on-one meetings. It was fun. So some things I've been getting into in recent times, RFID security and proxy re-encryption. So at Hopkins, as a visitor, I've been setting up an EE lab. We didn't have a grant at the time when I got started, so I went out to swap fests looking for oscilloscopes. I found an oscilloscope, but I couldn't figure out if it worked, so then I went out and looked for a function generator, to test it, and it worked, and I got a good deal. Didn't let the guy know, though, that I had a function generator. Otherwise, he would have bid it up, right? Oh, that would have been cool. Yeah. No, this is just a very boring function generator. I think it generated only, sine waves. I was basically trying to generate a carrier signal to excite some RFID transponders. So I spent some time tuning transponders and things, playing with inductors and coils and measuring Henrys and things like that. But then that relates to some work I've been doing in proxy re-encryption. So a step back, at Hopkins we worked on a file system. We were thinking, okay, how can we use untrusted servers to help us with access control? So if the publisher goes offline, can the publisher delegate to somebody else to control access to content? And yet that third party shouldn't get access to the plaintext, and they shouldn't get access to any kind of key material. So what our file system does, the third party can translate old ciphertexts into new ciphertext, basically. A publisher can delegate to the third party the ability to do this. Now, we've also been looking at how proxy re-encryption and proxy re-signatures may help in RFID security, because it turns out most of these RFID transponders are pretty dumb. Most don't have a battery. Most don't even have a processor. So we're thinking, okay, if an RFID tag could at least multiply, what could we even hope to get in terms of security? So we're trying to find out, in this model of where we have an untrusted third party, similar to, say, multi-party or server-rated computation, could you have this third party help you sort of beef up some kind of weak cryptographic computation done by an RFID chip. All right. So to wrap up, I talked about two things today, basically. How to provide authenticity of read-only content, where the publisher can update the content, but the client does not get to make a write back. And the goal was to make sure that we had high throughput even as content was changing. In the case of chefs, I talked about, well, how do we get access control, but in addition, how do we do that efficiently? So how can we get efficient membership eviction? Well, we do that using lazy revocation, and then efficient key distribution, minimizing the amount of keys using key regression. And then this is implemented, actually works, finally started to work on the Mac, and Linux finally started to work a few years ago. And I'd love to have a Windows implementation, but it's hard to find a Windows developer who also knows Unix. But with that, I'll take any questions. Thanks. I guess I'll find out what the smiles mean later.
They're not knowing smile. They're like,